Hi everyone, welcome back to Coding with Bharat channel. So as you know, we have been covering 2D prefix sum pattern and we have done already a few problems on it. So today we'll be taking up the last problem on this pattern that we had as of now, and basically go into depth of it. This one uses slightly more concepts from around the places, but yeah, I'll try to explain it in the best way possible. So let's just go ahead and get started. So the problem says we are given an m cross n binary matrix. So we have a binary matrix having ones and zeros. Now what we want to do is we want to find out the largest square in it. What is a square? The number of rows and number of columns in that sub matrix are equal. So we want to find the largest square in it which contains only ones. So as an example, if this is my matrix, then you can see that the one highlighted in green is a 2 cross 2 sub matrix, which is a square, right? The one highlighted in red is also such a matrix, but we could not take the combination of the two because it is rectangle and not a square, like 2 rows and 3 columns. That is not allowed. So you have to take a square and you have to find the largest one containing everything as 1. So everything has to be 1 here. Okay, so let's directly jump onto our whiteboard and try to figure out a logic for it. Okay, so let me go ahead and take a binary matrix. Let's take this. Okay, let's take this also. Cool. So I've taken this. I think probably everyone would have guessed it. The answer for this is actually going to be 3 because we have this 3 cross 3 matrix, right? Okay. Now, if we actually think about it, if we actually start with any I comma j, I'm talking about brute force here again. If we start with any I comma j, then in the brute force way, in the absolute brute force, what I can do is I can try to fix two more things, the length and the breadth, that how much length and how much breadth we take, and then try to run another loop to see if all things are 1 or not, right? This could be the absolute worst brute force, but you can obviously do some optimization on it, right? So basically I'm saying we'll write 5 loops. First loop to fix I, second loop to fix j, that is where we are starting our submatrix that we are fixing. 2 more loops to fix the number of rows and number of columns that we take in this submatrix. Last 5th loop to actually go on and check if all of them are 1 or not. So that would be the worst n to the power 5 solution, right? An n to the power 5 solution. But obviously this is pretty bad and we need to do much better than this. So first wasteful thing that we can see here, we are running 2 loops to fix length and breadth, that is number of rows and number of columns. But we are interested only in square submatrices, right? So since we are interested only in square submatrices, we can in fact replace this with a single loop of side. So again, 2 loops to fix I comma j. Okay, where is our starting point? Third loop to fix side. If you have the side, you know what is the submatrix that you are talking about. Fourth loop to actually go over the entire thing and see if all are 1 or not. So you'll see that drastically our complexity reduces to n to the power 4 because now we have reduced 1 more loop and the answer is 4 loops, right? So this is the maximum that we can do with just brute force ideas. Now we need to start thinking about some of the optimization approaches, right? Okay. Now, first thing that you can see here, we want to check if everything is 1 or not, right? And let's say the side is 3. If everything is 1, can I say that when I take sum of this square of side 3, then that sum would be equal to 9. That is 3 into 3. Why? Because if everything is 1, then that means there are, if S is the side, S square elements, all of them being 1, total sum, if you add all of them, all of these ones up, would be s square. So in a way, if you can quickly get the sum of any region of the matrix and compare it with s square after running 3 loops, then your job would be done. So if you know, this checking of sum of a region is the prefix sum that we have been doing so far. So if you optimize it, it would look something like this. That okay, we'll run first loop for I equal to 0 to n minus 1 to fix our first like row number of our first top left element. Okay, second loop j equal to 0 to m minus 1 to fix the column number. So we have row number, we have column number, so we have the exact element where our sub matrix that we are considering starts. Next, fix the side. So I'll say for s equal to, side could be 1, 2. For now I'll take minimum of n comma n, but we'll see also like how we can best estimate this, right? But right now I'm taking it minimum of n comma m. So I have the ij, I have the side. So what I can do, I can create that matrix, create that square actually, and find its sum of region. So what I'll do is I'll say, okay, bottom elements x is I plus s. So if side is, let's say 2, so, and we are at 0, so 0 plus 2 would give me the bottom x, right? Okay. Similarly, our bottom y would again look at j plus s. So we have the bottom x, we have the bottom y. Now I have the region, so I can just look at the sum of the region. So if sum of this region is what? ij to bottom x, bottom y. Okay, so let me move it around so that we can see the entire code. Okay, so if this sum of the region defined by ij and bottom x, bottom y, if that sum is equal to s square, then that means we are dealing with a square submatrix having all ones. So you can do answer equal to max of answer comma s. So just take the maximum of it. Obviously there are a few things missing here. This bottom x, bottom y can definitely go out of bound, like adding I plus s can take out of bound, and similarly j plus s can also take out of bound. So to improve that, what we can do is we can in fact replace this with making sure that our side length doesn't go beyond the maximum side length that is possible. So let's calculate what is the maximum side length which is possible. Maximum side length. So if we were dealing with I equal to 0, then we can in fact take number of rows till n. If we are dealing with 1, then we can take the side length only at max as n minus 1. So I can say n minus I and m minus j, out of this the minimum. So maximum side length would be equal to minimum of n minus I and m minus j. N is the total rows possible. If you are at row number already 1, that means you cannot take one row. You can at max take n minus 1 rows. Similarly, if you are, let's say, at column number 3, that means 0, 1, 2 are on the left side. So you cannot take those. So you can just take from 3 till the last. So m minus 3 would give you that, okay, we are removing this 0, 1 and 2. Cool. So this is the maximum side length. So we'll just iterate till this maximum side length, and that will make sure that these two do not go over the boundaries. Okay. So with this idea and with our prefix sum, we'll be able to reduce it to n cube. Okay, we'll be able to reduce it to n cube because 2 loops for ij and third loop for side length. But even this is not enough, right? We had to do better than n cube and come up with a much more solid approach. So here comes another pattern into the picture. I don't think we have covered it on the platform, but if you have been doing programming for a while, you will understand it. You can still try, even if you don't know this new pattern, you can still try submitting this much with your prefix sum and you should be good. It might also get accepted. Like, so I saw the ranges and the ranges were not super high. Yeah, it's only 300. So even n cube with 300 is what? 3 into 3 into 3, which is 27 into 10 to the power 6. So almost on the borderline, but it might pass, right? So you can try this out. Uh, okay, let's also try to understand this new approach or new pattern that we have not seen so far, which is binary search on answer. Okay, so let's take an example. So let's say we have something like this, right? Here we can clearly see that for 3 cross 3, our answer is yes. Now, if I try to ask the same question for a smaller size, let's say 2 cross 2 or 1 cross 1, keeping I comma j same, can I say the answer will always be yes? Whatever is your answer, anything smaller than that would be yes. And anything more than that, so if there was one more layer here, the only reason that you will not get 4 into 4 is if at least one element is 0. So in a way, what I'm saying is, if your answer is some side length s, anything smaller than s, your answer will always be also yes. Like if I ask you, if the condition follows, what is the condition? That some of the elements in that range are equal to side into side. So if we check that, for 1 into 1, answer is yes. 2 into 2, sum is 4, which is 2 into 2. For 3 into 3 also, sum is 9, which is true. 4 into 4, if you look at it, it would be 15. There are 15 ones, not 16. So answer will be no. So anything, so whatever is your answer, anything less than equal to that answer, you get a yes, that okay, that has all ones. Anything greater than that will be a no. Anything greater than that. So 4 answer is no, 5 answer will always be no, because if even one of them is 0, then the answer becomes no. This pattern where your answer for something is yes, 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 where you are keep on increasing some value, the answer keeps on staying yes, then it goes no and stays no forever. This kind of pattern or these kind of functions are known as monotonic in nature. So what are monotonic functions? Monotonic functions are essentially increasing or decreasing. So if this function we talk about, it stays 1, which is yes, 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 and then it goes 0. So it's a decreasing function. So for any of such functions which are increasing or decreasing in nature, you can use binary search to figure out. How would you use binary search? You would simply say that, okay, right now what I'm doing in my code, I am iterating that, okay, side length is 1, side length is 2, side length is 3, side length is 4. I'm going one by one, and till the time I get yes, I'm updating it. I'll not do this now anymore. I'll say, I'll find my minimum, I'll find my maximum, check the middle element, right? Check if middle element satisfies this condition. If middle element satisfies this condition, then that means till mid, I can make any smaller submatrix and I'll try to find a bigger answer. But if at mid I see that, okay, this condition doesn't satisfy, that means there is at least 1 0 till mid. So I'll try to shorten and try to find a smaller answer. And that is the main idea of using binary search here. So let's see it in the form of code as well, quickly. Okay, so I'll walk over the entire code. By the way, these two, calculate prefix sum and sum of region, we have been doing throughout the entire playlist, right? So I'm not going to repeat them. Just to shorten what we do here, when we do calculate prefix sum, we take sum row wise sum, column wise sum, we get the prefix sum array, 2D array. Then we do sum of region. What do? Whenever we want to calculate the sum of any region, We take the bottom right sum from start till this bottom right, then remove the extra rows at the top, remove the extra columns on the left, and add back the small square that we will get common in these two removed parts. So yeah, again, check out the first video in this playlist if you are not aware of this pattern as of now. Okay, so these two I'm not going to repeat. I'll go over the remaining portions. So first thing what I'm doing is I'm getting this matrix which is 0 1 matrix, but you can see that it's character 0 or 1. So I'm converting it into integer matrix. So you'll see that I create a new p sum matrix of the same size, and I simply update p sum ij is equal to matrix ij minus 0. So minus 0, if it's 0, 0 minus 0 will be 0. If it's 1, then 1 minus 0 will be 1. So at the end, I'll end up getting the actual integer here. By the way, this is ASCII difference, right? You might ask that why did not we copy? Because then the ASCII value would be copied when we do character to int. What I want to do is I want to convert it into actual integers. So that is why I'm doing this minus. Okay. So now that I have this prefix sum, no, not the exact prefix sum, but the matrix of ones and zeros which are in integer form, I can actually calculate the prefix sum. So I call this function to calculate prefix sum on this array. Okay. Now what I want to do, I want to go over each of the elements and put them as the top left and find out what is the maximum square that can be formed from there. So I'll do answer equal to 0. I'll go over every ij. So this is same. I'm going over every ij. If the element at I comma j is 0, right? If at any place there is 0, like for example, if we try to start our sum matrix as this point, even 1 cross 1 is not possible, right? Forget about 2 cross 2 or bigger matrices. Even 1 cross 1 is not possible. So we need to ignore all the 0 cases. We just are going to focus on wherever there is a 1, because there is a chance that we would be getting a sum matrix out of it. Okay. So I'm saying wherever there is a 1, calculate the answer for this I comma j and take the max of it, right? So this is pretty straightforward. Calculate is the main function which is doing our job, which is giving us the maximal square, keeping I comma j as the top left. Okay, so let's look at how maximal square is implemented. This actually implements our binary search logic. So let's see that in action. So this calculate, if you see, has I comma j where we are starting and the prefix sum. So what I am doing is minimum side length is 1, right? Because 1 cross 1 we have already seen is 1, because it doesn't start with 0. So 1 cross 1 is already 1. So we can take the minimum side length as 1. Maximum side length, this you can see, this is what? N minus I and M minus J. So you can see it here as well. We calculated it, right? Where did we calculate it? We did calculate it at some point. Yeah, here. So you can see maximum side, I told you, minimum of N minus I, because those extra I are removed. So N minus I and M minus J, right? So same idea here. Minimum of P sum minus I and P sum 0 minus J. Okay. Let's go ahead then. So then we say answer is 1, because we have seen minimum side length is 1. So we'll keep answer as 1. Now I know the minimum side length and maximum side length. So I'm using binary search. So while L less than equal to R, this is standard binary search, right? While L less than equal to R, find the mid. Okay. What is this mid? This mid is in fact the side length that you are trying to calculate the answer for. That okay, if mid is, let's say, 5, then starting at I comma j, if I take 5 cross 5, will it be all 1 or will it not be all 1, right? So first thing I need to calculate, what are the bottom right elements? So I'm saying I plus mid minus 1, j plus mid minus 1. So to get the bottom right, so I have top left, I have bottom right, I can calculate its sum. So I'm saying if sum of this region of prefix sum from I comma j to bottom x bottom y, if this sum of this region is equal to mid into mid. So what is our mid? Our side length. So if it is equal to the square of the side, then we put it as answer and try to find a bigger answer. So we say L equal to mid plus 1. So only look for the remaining range on the right side. Otherwise, if the answer is not equal to side into side, we'll find a smaller solution. So we'll say R equal to mid minus 1. So just replacing that linear search that we were doing one by one to a binary search where we find mid and then decide whether to go left or right. Okay. So with this, we have reduced our third loop, which was of on, to log n. So our complexity becomes n square into log n. Okay. Great. So that was the whole idea of this problem. Do implement it out. It is a very nice problem to try out. And this pattern is actually very common as well. So if nothing new comes up in this week's weekly contest, probably I'll take a binary search on answer as the next pattern for next week, right? So yeah, see you guys for the remaining videos of the week. Bye bye. Do like the video and subscribe to the channel if you're new here, and share it with your friends if that is possible. Great, then see you tomorrow. Bye bye.